Welcome back. This is Plan B of the Probability 2 Relationships Between Events video. This is the one where I'm solo lecturing. So I'm gonna talk about this Lego example, and we're gonna discuss some probabilities that we can calculate from this example, and we're gonna discuss the relationships and interrelationships between different sorts of events that are measuring the same kind of outcome. So let's do some simple examples here. Let me explain what I've got here. I've got a diagram of a collection of Legos. Some Legos are red, blue, pink, green, and orange, and some of them are big and some of them are small. So I've got a big Venn diagram here. The big ones are across here, the small ones are here, and we want to measure the probability of various events. So first I'm just going to do some various examples here in order to illustrate that we can measure these probabilities by counting, just like in the last video. So if we have the probability of red and we want to calculate that, we count up how many are red. There are 8. And we divide by the total number of Legos, which is 20, trust me, or recount for yourself here. And we get 0.4 or 40%. If we want the probability of the Lego being big, then we count up how many are big. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And divide by the total, which is 20. And that's 1/2 or 0.5 or 50%. Now we can also ask more refined questions here. We can ask, for example, for the probability of being big and red, which would be 4 out of 20 because there are only 4 Legos which are both big and red. And that would be 0.2 or 20%. We can ask for the probability of being small and blue, and that would be 2 out of 20 or 10% or 0.1. So because they're, sorry, I did that wrong. That would be 1 because there's only one that is both small and red. And so that would be 0.05 or 5%. So that's this one. There's only one that is small and blue, as asked here. Okay, so this is how we can calculate the various probabilities of individual simple events. But these events can be interrelated. And let me point out something. There are 2 kinds of relationships that we want to discuss today. Today, we want to discuss the relationship of being disjoint, which is also called mutually exclusive. And we want to discuss the relationship of being independent. And these are 2 different kinds of relationships. So let's talk about disjoint first. So relationships can be disjoint. Or this is also called mutually exclusive. If you have a property of Legos that you're trying to measure, like being pink, and another property of Legos that you're trying to measure, like being green, then in this collection, there are no Legos which are both pink and green. And so those 2 conditions, they cannot both happen. They don't have any overlap. And so we'll call those disjoint or mutually exclusive. So no overlap, which is the same as saying they can't both happen. Another case of this that you might see here in this Venn diagram is the property of being small and the property of being pink. Although I've illustrated an overlapping region in the Venn diagram, there are no actual small pink Legos represented in this collection. And so pink and small are mutually exclusive in this case. Now, when events are mutually exclusive, it's really easy to relate their probabilities. So, well, it's not easy to, it's easy to calculate the probability of being both or one or the other of them. So let me illustrate. So the probability of being pink is 1 in 20, which is 0.05. The probability of being small is 10 in 20, or 0.5. So from this information, it's very, and without even referring back to the picture, it's very easy to assess the probability of being pink and small. So the probability, well, if we know that they're disjoint. So the probability of being pink and small, if we know that they are disjoint, is going to be 0. Because that's what disjoint means, effectively. So this is because they're disjoint. If these events are indeed disjoint, and they are, there are no pink small Legos here, then the probability of being both is 0. So that's easy. We can also assess the probability of being pink or small. Here, the probability of being pink is 0.05. The probability of being small is 0.5. We add them together and we get 0.55. Now, just adding them together here really requires that they be disjoint. Otherwise, adding them together is not exactly the right thing to do. But if events are disjoint and you want the probability of one or the other, then you can just add the two probabilities together. So this is what disjoint or mutually exclusive means, and this is how we can combine probabilities to get probabilities of interrelated events, like being both of them or one or the other of them. The next interrelationship between kinds of events that we want to talk about is the relationship of being dependent or independent between events. So, here, to illustrate this, notice that there are two large blues and only one small. And it's the opposite situation with green. There's one large green and two small greens. Now, if you draw a Lego and you know that it's blue, then that does actually tell you something about its size. There's some sort of relationship there. It's more likely to be large than small. If you draw a Lego and find that it's green, then it's more likely to be small than large. And so there's a relationship between the color blue set and the size information. However, there is no such relationship for the red. Exactly 10 of these are large overall, exactly 10 are small. And among the reds, they are balanced, 4 large and 4 small. If I draw a Lego and find that it's red, that gives me no information at all about its size. If I draw a Lego and know that it's big, I don't know that it's more likely to be red or less likely to be red. It's going to be 40% either way. So this relationship that there is no relationship between the two events is called independent. So let me state that more carefully, and then we'll talk about how it helps us calculate things. So events are independent if they are probabilistically unrelated. Not associated or not correlated. Basically, there isn't a relationship between the various probabilities involved. So, for example, the probability of red and the probability of big. So I should say red and big in this example are independent. There's no relationship between those events. Now, when events are independent, let me remind you, the probability of red is 20%, 0.2. Sorry, I did that wrong. The probability of red is 8 over 20, which is 0.4. The probability of big is 10 over 20, which is 0.5. And now let's calculate two other probabilities here. The probability of being red and big, and the probability of being red or big. The probability of being red and big is 4 out of 20, which is equal to 0.2 or 20%. The probability of being red or big, now this has to be calculated carefully here. It's 1, 2, 3, 4 plus the 10 that are large. And so that's 14 out of 20, which is 0.7 or 70%. Now, what do we need to notice about these probabilities? The key thing that we need to notice is a relationship between these three. There is a key rule here represented by these three. That is that the probability of being both red and big is the product of the two probabilities. 0.4 times 0.5 is 0.2. So for independent events, we have this rule. The probability of A and B is the probability of A times the probability of B. And now I want to point out that, so I'm not giving you a rule for how to get this. There is a slightly more complicated rule for how to get the OR of the two events, how to get this probability. That's not so important right now, but what I want you to really notice here is the probability of being red or big is not the sum of the two probabilities, right? So I just erased a formula for disjoint events that said the probability of doing this or that is the sum of the two. And now I'm saying, oh no, that's not true. Why not? Well, because that formula was for disjoint events and this formula is going to be for independent events. So I want you to notice that we can't just always add the probabilities. If the events are independent, or more generally, if they're not disjoint, then getting the probability of A or B by adding the two probabilities is not the right thing to do. And so here, notice we're not getting 0.9, which would be what happens when we add them. So events can have various kinds of relationships to each other. And based on those relationships, we have various kinds of formulas that help us calculate the probability of various combinations of those events. This may be one of the most important formulas because this allows us to calculate the probability of very complicated things. Supposing I roll 3 six-sided dice and then draw a card from the deck. What's the probability that I get a 1 and a 5 and a 6 and then draw the ace of clubs? Well, in order to calculate that, I need to look at this event and this event and this event and this event, and I need to think of them as different, separate, independent events, each one of which has their own probability. What's the probability that they all land in a certain way? Well, it's just a product of those events. And so we often use this to calculate the probability of very complicated combinations of independent events by simply multiplying the probabilities.